This is a video from section 4.4. We're going to look at problem 2a. It says determine whether the vectors are linearly independent or linearly dependent in R3. And we're going to look at the vectors -3, 0, 4, 5, -1, 2, and 1, 1, 3. And so we're going to take a linear combination of those three vectors and set it equal to 0, 0, 0. In other words, we're going to take a linear combination of those three vectors and set it equal to the 0 vector. And we want to show, if possible, that C1, C2, and C3 have absolutely no choice but to be 0. And that'll prove that the vectors are linearly independent. If I find an alternative solution, then the vectors are linearly dependent. So let's go ahead and get started here, and I'll show you what I'm talking about. So we're going to take C1 times the vector -3, 0, 4, plus C2 times the vector 5, -1, 2, plus C3 times the vector 1, 1, 3, and we're going to set it equal to 0, 0, 0. And this right here is going to produce a system of equations. So I'm going to take C1 times -3 plus C2 times 5 plus C3 times 1, and I'm going to set it equal to 0, the first component. I'm going to take C1 times 0 plus C2 times -1 plus C3 times 1, and I'm going to set it equal to the second component of 0. And then I take C1 times 4 plus C2 times 2 plus C3 times 3 and set it equal to 0. So I'm equating components, in other words. And that's what I do here. So I get -3C1 plus 5C2 plus 1C3 equals 0. 0C1 minus 1C2 plus 1C3 equals 0. And 4C1 plus 2C2 plus 3C3 equals 0. And so I'm going to write this system in matrix form. So I'm going to take the coefficient matrix -3, 5, 1, 0, -1, 1, 4, 2, 3. I'm going to multiply by the vector C1, C2, C3, and I'm going to set it equal to the 0 vector. So the column vector is 0, 0, 0. Now, we're going to let A equal the coefficient matrix, -3, 5, 1, 0, -1, 1, 4, 2, 3. And it turns out, if we take the determinant of A, we get a number that is not equal to 0. And so what that proves is A is invertible. And we have a theorem that says if A is invertible, then this system only has the trivial solution, which you will see shortly. So if I go to the next page, I claim that the vector C1, C2, C3 is the inverse of the coefficient matrix -3, 5, 1, 0, -1, 1, 4, 2, 3 times the 0 vector. But that's the 0 vector. And so what that says is C1, C2, C3 are all the same, and in fact, they must equal 0. And that proves that the vectors -3, 0, 4, 5, -1, 2, and 1, 1, 3 are linearly independent. Now, let me backtrack a step here. And so when I have A times the column vector C equal to the 0 vector, now we just showed that A is invertible. And so I can multiply both sides by A inverse. Oh, let's go back. But remember that A inverse times the 0 vector is just the 0 vector. That's the left side. And then I'm going to shift parentheses and say A inverse times A times C But A inverse times A is the identity matrix. So I have the identity matrix times C is equal to the 0 vector. But what that says is that C is the 0 vector. And that will concretely show that C1, C2, C3 all have to be 0. And so therefore, since that's the case, all three of those vectors are linearly independent in R3. And so what that basically means is that one vector cannot be written as a linear combination of the other two vectors. Let's look at 5a. It says, determine whether the matrices are linearly independent or linearly dependent. This is another great exercise. Suppose we have the first matrix, which is 1, 0, 1, 2, the second matrix, which is 1, 2, 2, 1, and the third matrix, which is 0, 1, 2, 1, and these are all in the set of all 2 by 2 matrices. So I'm going to take a linear combination of these three matrices and set it equal to the 0 matrix. And that's how these work. Okay, that's how you show linearly independent or linearly dependent. So in other words, I'm going to take C1 times the first matrix plus C2 times the second matrix plus C3 times the third matrix, and I'm going to set it equal to the 0 matrix. And that's going to produce a system of equations. Now, I'm equating entries, corresponding entries, in fact. So I'm taking C1 times 1 plus C2 times 1 plus C3 times 0, and I'm going to set it equal to 0. That's the first equation. Then I'm going to do C1 times 0 plus 2C2 plus C3 equal to 0. That's the second equation. And in a similar fashion, I can say C1 plus 2C2 plus 2C3 equals 0, and 2C1 plus C2 plus C3 equals 0. And so I have a system of equations. I have 4 equations with 3 unknowns. That's over here. And so I set up the corresponding matrix equation. So I'm going to take the coefficient matrix 1, 1, 0, 0, 2, 1, 1, 2, 2, 2, 1, 1, times the column vector C1, C2, C3, and I'm going to set it equal to 0, 0, 0, 0. And from here, I set up the augmented matrix. That's down here. And then I perform a series of elementary row operations. So you got to remember the coefficient matrix is not square. And so we don't have the determinant at our disposal. If we had the determinant at our disposal, this would be a much simpler problem, by the way. And so I did a bunch of row operations for the next few pages, okay? And I arrived, taking my time here, and let you guys absorb this. I arrived at this matrix, and this is in row echelon form. And from here, I wrote the corresponding system. You notice how I have a row of zeros at the bottom. And so the first equation is C1 plus C2 equals 0. The second equation is C2 plus 2C3 equals 0. The third equation is C3 equals 0. And because C3 equals 0, we're guaranteed that C1 and C2 also have to be 0. And what this says is the three matrices are linearly independent in the set of all 2 by 2 matrices. That concludes this video for section 4.4, where we looked at problems 2A and 5A. Thank you.